Today, we are going to look at this question from the 2020 Indian National Mathematical Olympiad. We have the set of integers x from 0 to 9. The question asks for a subset S of x such that any positive integer n can be written as p plus q, where the non-negative integers pq have all their digits in S. We have to find the smallest possible number of elements in S. When it comes to finding the smallest set, a usual line of attack is to first find a set which has the desired property we want, and secondly, to prove that no other set with a smaller size works. Before we do any of that, let's play around with a problem a bit to see if we can get any low-hanging fruits. Let's consider how can we write 1 as p plus q. In this case, the one and only possibility is to write 1 equals 1 plus 0. So straight away, we get a mini victory, as our subset S must contain 0 and 1. Clearly, 0 and 1 is not enough, since there's no way we can write 5 as p plus q, let's say, using only the digits 0 and 1. So we can draw the conclusion that the size of S is at least 3. Not too bad for a few seconds of work. Next, let's make an observation. We can actually focus our attention on the units digit alone. If we can make every number from 0 to 9 by adding up two numbers from our subset S without carrying over 1, then we have actually solved the problem for any given positive integer n. This is because after we find the two numbers which add up to the units digit without carry over a 1, we can repeat the same operations with the tens digit, the hundreds digit, the thousands digit, and so on. For an n digit number, we are essentially dividing up the question to n separate digits, chunks, where each chunk can be solved independently before putting them together to get one final answer. Granted, we still have to prove that the size of S is indeed the minimum possible, but if we can find a set, then at least we have an upper bound to work with. We already know that 0 and 1 must be in our subset S. Using these digits, we can make 0, 1, and 2. What about 3? If we add 2 to the subset S, then sure, doing this allows us to write 3 as 1 plus 2. But 2 seems a bit redundant, as we can already get a 2 by adding 1 to 1. Let's include 3 in our subset S instead. By doing so, we can express 3 as 0 plus 3, 4 as 1 plus 3, and 6 as 3 plus 3. We can continue follow this algorithm, adding new numbers to S, which will maximize the number of integers we can make using the new number together with the existing integers in S. With 0, 1, 3 already in S, we see that adding the number 4 to the set S allows us to get 3 more numbers, namely 5, 7, and 8, and this is the most we can get. This approach of selecting the element which maximizes a certain quantity at each step of the selection process is called the greedy approach, and this is a powerful idea which has wide-ranging applications from the fields of mathematics to computer science. Anyway, the greedy algorithm actually doesn't help with this problem that much. I use it just because I want to demonstrate it to you. After selecting 0, 1, 3, 4 into our set S, we see that we can create all the numbers from 0 to 9, with the exception of 9. At this stage, we can select any number we like, as long as the inclusion of the number allows us to get 9. Let's go with 5, just for the sake of it. So, given any number, let's say 31,415, what we do is we focus on the digit one by one, and find two numbers which add up to the digit. For 3, we can pick 1 plus 2. For 1, we can use 1 plus 0. For 4, maybe 2 plus 2. For 1 again, 0 plus 1. And for 5, let's go with 2 plus 3. Combining this gives us 11,202 plus 20,213 as required. So we have proven that a subset with 5 numbers work. Earlier, we have shown that since 0 and 1 must be in S, and that having 0 and 1 obviously doesn't work, we are looking at the bound, the size of S between 3 and 5 inclusive. We now need to show that any set with 3 or 4 elements wouldn't do the job. We actually have quite a lot of tools at our disposal at this stage. We can try the brute force approach by listing down every possible 3 and 4 element subset and prove that none work. But this proof by exhaustion approach isn't very elegant and is rather time consuming. Rather, let's try our hand at continue building the set S, assuming that it now only has 0 and 1 in it. The only two ways to express 3 as p plus q would be either 0 plus 3 or 1 plus 2. So we know that either 2 or 3 has to be in our set S. However, neither of these set works, as there's no way to make the digit 9, say. Would adding an extra element solve the problem? At this stage, since we already have 3 elements in the set 0, 1, 2, there are only 7 cases to check if we resort to brute force. By listing down all possibilities, we see that there's no possible set S with 4 elements, which will allow us to express any positive number as p plus q, using only the numbers in S, as there are always some missing numbers which cannot be created. Doing the same thing to the set 0, 1, 3 gives the same result. So now we can conclude that the smallest size of S which works is 5. And earlier we gave a construction, which is a set 0, 1, 3, 4, 5. Let's recap the ideas we have used in solving the question. Overall, I would say that playing with the small numbers like 1, 2, 3 allows us to draw conclusions about certain numbers which need to be present in the set S. The other important idea would be the divide and conquer method earlier, where we break out the digits and find two numbers which add up to each digit independently before combining the answers. Doing so, we see that it is sufficient for us to create a set S from which we can derive the integers 0 to 9 by pairwise addition. In mathematics, by dividing up a complicated problem into smaller chunks, sometimes we can substantially simplify the problem. And this question is a good example. Alright, we have come to the end of the video, and I hope to see you in the next one. Till then.